Hello everyone. This is part 2 of polar coordinates. And last time we saw the theory behind polar coordinates and how to convert points from polar form to rectangular form and vice versa. But you're not going to be tested on that conversion of points. If you look at the final exam topic sheet posted in Blackboard, as I mentioned before, under polar coordinates part 3, you can see we're going to convert equations from polar to rectangular and vice versa, one question of each, worth 6 points each. So here's a couple examples of each of those. To convert the equations, you want to always look out for x squared plus y squared, because immediately you could replace that by r squared. That's something very important in polar coordinates. As you move on to calculus 3, you'll see this come into play quite often whenever you have a quantity x squared plus y squared involved, some form of a circle basically. You're going to want to use polar coordinates. But in any event, look out for x squared plus y squared and replace it by r squared right away. X we could replace by r cosine theta and y by r sine theta. The idea though is we want r in terms of theta, just like you get a function y in terms of x. So here's an example where immediately we see we could replace the x squared plus y squared by r squared. And then the only other thing we could do is replace the y by r sine of theta, and that's equal to 0. And now solve the resulting equation for r. So you can factor out an r. You have r minus 2 sine theta. Set each to 0. And r equaling 0 is trivial. So the equation here transposing the negative 2 cosine theta, or negative 2 sine theta, excuse me, r equaling 2 sine theta would be our equation. And it's kind of interesting to see how that gives us the equation of this shape, which we can recognize as being a circle because x and y are both squared and the coefficients are equal and positive. Okay, so here's another one. No r squared, no x squared plus around. All we could do is replace x by r cosine theta and y by r sine theta. And then we have minus 2 equaling 0. Should be obvious, you don't want to write these 3 equations down on your cheat sheet for the final exam. Okay, now we need to solve for r, so we'll transpose the 2. So for r cosine theta plus 7r sine theta is 2. Factor out the r. I suppose we could have done that in the same step. 4 cosine theta plus 7 sine of theta equals 2, and then divide by what's in parentheses on the left. So we get a fraction, 2 in the numerator, and what's in the left in parentheses in the denominator. Okay, so that's kind of interesting that that's the shape, that's the equation. Kind of complicated. That gives us a straight line, because obviously we recognize this as being a straight line. Okay, so there's a couple examples of converting from rectangular to polar, and I'll go in the opposite direction, converting from polar to rectangular. And we still want to consider the r squared as x squared plus y squared. So if you ever see an r squared around, replace it by x squared plus y squared. But because we're going to be given a function in terms of r and theta, you could replace cosines by x over r and sines by y over r. So again, equations that you're going to want to include on your cheat sheet. And you don't necessarily have to solve for y in terms of x, but you want to get an equation explicitly in terms of x and y in probably a standard form. Okay, so all we can do here, whatever you do, never try to force an r squared to exist. Either wait for it to appear or wait for it to disappear. but never force it. What I mean is, don't square both sides of this equation just for the sake of creating an r squared. Just be patient, and maybe something nice will happen. The only thing we could do then, if we're going to save that r, is replace cosine by x over r. Okay, so let me rewrite this. R equals 4x over r. And then from here, you could think of either cross multiplying, put this over 1, or multiplying both sides by r. But however you think of it, we then get r squared equals 4x. And now we see the r squared, which we could replace by x squared plus y squared. So x squared plus y squared is 4x, and we're done, because that's a form that gives us the equation of a circle. Alright, so now in this example, again, don't want to square both sides. Let's just wait and see what happens. Leave the r to begin with. Only thing we could do is replace the sine of theta by y over r, and the cosine of theta by x over r. Okay, if you want to take a step and rewrite this, you don't have to, but I'm going to say 2 over 5y over r minus 7x over r. Okay, and at that point, on the right-hand side, we have a complex fraction. That is, we have these fractions within the overall fraction. So let's get rid of the fraction, the complex fraction, by multiplying the numerator and denominator by the least common denominator between all of these three terms, which is just simply r. And so on the left we have r. On the right, we now have 2r over, when we distribute this r in the denominator, times 5y over r, the r's canceled, that's why we did it. And similarly, when we multiply the r by 7x over r, the r's cancel and we just get 7x. And now we can see that r is a common factor to both sides, so you could either divide both sides by r or just simply think of canceling out the r. And we get that 1 is equal to 2 over 5y minus 7x. And now think of cross multiplying or multiplying both sides by 5y minus 7x, and we get 5y minus 7x is 2. And that's sufficient. You could solve for y in terms of x, but that's certainly the equation of a straight line, and so you could leave it at that. Alright, so that would be 12 points between those four problems, one of each type. Okay, next we're going to look at graphing polar equations. I'm not going to require you to graph. Your graphing calculator, actually, if you have a TI-83 or some graphing calculator, you can actually change the mode to polar form, and it'll graph these equations just like it graphs equations in the Cartesian system. But you have to give the equation for r in terms of theta. Before we look at the common polar graphs at the bottom here, there's a what you want to do to graph the polar equations initially, because you won't, when you don't know how to graph an equation, what did we do? Well, we just created a table of x and y values, and that's what we're going to do here. But we're going to choose our thetas and calculate r, and then we plot the points. Now there's a document to make things easier. I created this document that's in Blackboard, posted in the Parametric Equations and Polar Coordinates handout folder in the Final Exam New Topics and More folder. So this is the main folder to go to for the final exam, where it says Final Exam New Topics and More. So there's this subfolder, Parametric Equations and Polar Coordinate Handouts, and within that is the polar graphs with tables. I think the polar paper's in there as well, as mentioned earlier. But in any event, this is what it looks like. I've got some graphs of polar. I've got some polar graphs. Okay, polar coordinate system not filled in. And then to the left is I created some tables of values. So just to save some time, So we're going to go through these three graphs, and then we'll come back and talk about the general forms for the equations. So our first graph. All we're doing is picking values of theta, and one guideline is to pick theta so that the angle that you're dealing with is a multiple of 30 degrees. That's just for the sake of, graphing some nice points. Doesn't have to be, but it's just a guideline. But that's what I followed here. Since the argument was just theta, I chose multiples of 30 degrees. And all we're doing is we're plugging in the value of the value of theta. So this is like, for example, here is 2 cosine 0 degrees. And cosine 0 is 1, so 2 times 1 is 2. Here's 2, here, let me do this. The square root of 3 is approximately 1.7. But that came from 2 times the cosine of 30 degrees. And cosine of 30 is radical 3 over 2. So that's how I got the radical 3. And probably convert it to 1.7 so we can plot it efficiently. Here's 2 cosine 60 degrees. Cosine 60 is 1/2, so 2 times 1/2 is 1, etc. Okay, so if you had to do this on your own, just pick values of theta, plug them in, calculate the value of r, create your little table, and then plot the points. So let's plot the points and see the shape we get here. So, where everything crosses right at the center there, that's not called the origin. It's called the pole. Okay, is analogous to the origin. But in any event, okay, so 0 degrees, 2 units. So in the 0 degree radial line direction, 2 units, that's right around there. That's right there. 30 degrees, 1.7, maybe right around there. 60 degrees, 1, so along the 60 degree radial line, there's 1. 90 degrees, 0, so we're at the pole. 120 degrees, -1, so in the 120 degree radial line, opposite 1 unit. So along the 300 degree radial line, 1 unit. 150, negative radical 3, or it's about negative 1.7 again. So along the 150, but opposite would be along 330, about 1.7, so right around there. And then 180 brings us -2 units, so opposite along the 0 degree, 2 units brings us back to our initial point. You can plot other points if you want, but basically what we're going to see out of this is just a simple graph of a circle. Okay, so circles, we'll talk about the general form for a circle. And if we have more time, we'd memorize the forms, but here just seeing the different shapes. So you're probably saying, well, what's the big deal? Why can't we use Cartesian coordinates? We know what a circle looks like and how we can plot it. Well, the big deal about polar is that there's some unique graphs, like the following 2 examples, that you can't obtain easily in the Cartesian system. I separated this into 4 pieces, as we're going to see why momentarily once we see the graph, what the graph looks like. And because the argument was 2 theta, I chose theta to be multiples of 15 degrees, so that the angle was multiples of 30 degrees. So this can make for a nice accurate sketch. Okay, at 0 degrees it's 0, so that's the pole. At 15 degrees it's 1.5, so halfway between 0 and 30, 1.5, right around there. At 30 degrees it's 2.6, so kind of guesstimating right around there. At 45 degrees it's 3, so halfway between 30 and 60. At 60 degrees it's 2.6 again, so right around there. At 75, halfway between 60 and 90, it's 1.5, so right around there. And then back to the pole. So if you can plot more if you want, but this is the general shape for that piece in the first quadrant, if you will. Okay, so that's what that looks like. Okay, so let's go to this one. I'll keep the angles as being positive for now, or the radii to be positive. All right, now let's do the negative one for fun. 105 degrees. Opposite of 105 would be 285, 1.5 units, right around there. 120, but opposite 2.6, right around here, so 300 degrees. 135, but opposite 315, 3 units. 150, opposite 330, 2.6 units. 165, opposite about 345, 1.5 units, and then back to the pole. At 180, we're at 0 again. So then the shape here is essentially the same shape that we saw in the first quadrant. And it basically repeats itself in the second and third. So I'm drawing the extreme values, and you could draw these little propeller looking things. Okay. And so these propeller looking things, I look at them and I see a propeller like on a airplane. Old airplane's propeller. But these are referred to as petals, P-T-A-L-S, like the petals on a flower. And because it has that shape, okay, that almost looks like a flower, mathematicians have given this a special name. It's what's called a rose curve. Okay, so that's a special shape that you can't really get in the Cartesian system easily. And there's another shape here that isn't easily generated in the Cartesian system. So I chose a bigger graph because we're going to need it. Let's just start going through and plotting the points. 0 degrees, 4 units, so 0, 1, 2, 3, 4 right here. 30 degrees, these do have 30 degree radial increments, so 30 degrees, 3.7, right around there. 45 degrees, 3.4, so right around there. 60 degrees, it's 3, so right there. 90 degrees, it's 2, so here. 120 degrees, it's 1, so right there. And what's happening at this point is it's starting to spiral in. That is at 135, halfway between 120 and 150, it's 0.6, so right around there. And then at 150, it's 0.3, so it's spiraling into the pole. Then finally at 180, it's at the pole. So this piece takes this shape where it's kind of spiraling in here to the pole. Okay. And then if you plot the other points, basically you'll see that it spirals out. At 210, it's 0.3. 225, it's 0.6. 240, it's 1. 270, it's 2. 300, it's 3. 315, 3.4, 330, 3.7, and then 360 back to 4. So then it takes the shape where it spirals out and comes back to where it started. Okay, so hopefully you can see that. The way I've darkened it up there. Yeah, you can see that pretty good. And it pretty much looks like this, right? So something like that. And mathematicians have given this a name as well because of the peculiar shape. We've named it as a body part, and you can kind of guess as to what that looks like. Hopefully you're thinking of turning it this way and seeing a heart. Okay, so get your minds out of the gutter if you saw something else. So because it looks like a heart, we call it a cardioid. Okay, so those are special graphs that you can't get in the Cartesian system easily. I'm not going to hold you to graphing. Again, your graphing calculator will graph these for you, but you do want to know about rose curves and cardioids. And there's even another one that's kind of special I'll mention here. I did summarize on that last page we were on where we converted the equations. I gave a summary of all the different common polar graphs that you can encounter. The circle, rose curve, cardioid, and what's called the limacon. But you can see the circles. You can, if r equals a, that's just a circle centered at the origin. Like if r is 2, it's just a radius of 2, right? If r is a sine of theta, well, here, if r is a cosine of theta, we get a center of a over 2. So that's what we had here. There was the value a over 2, half the radius at 1. So at 1, 0. If you wanted the circle with the center on the 90, 270 axis, that's when you would use the sine function. So those are different equations for the circle. For the rose curve, okay, you've got either cosine n theta or sine n theta. We had, what did we have? We had sine n theta. And so it's n petals if n is odd, and 2n petals if n is even. So Rn was even, so we had 2 times 2 or 4 petals. So, and if we're, notice how we're in the quadrants, so to speak, quadrants. When you've got the sine, if you dealt with the cosine function, they'd be on the axes, so they'd look more like this. That's if it's this would be r equaling, let's say, 3 cosine of 2 theta. Oops, you didn't see that, sorry. So I was drawing it down there. They would be on the axes. The propellers would be half instead of in the quadrants explicitly. Then we have the cardioid. Kind of interesting, just the fact that, you added just one number to the circle, 2 cosine theta, and it created that little dimple effect. Okay, they give you that, a cardioidal shape, right? So kind of interesting there how that minor effect does that. And then you've got the limacon, and the limacon is when these numbers are different. Then what's generated, even more interesting, is you get the cardioid, but you actually get a little loop inside of it. Okay, and there are other graphs. There's spirals, and, but all of them take those types of curve, have those special types of curvature. So we don't have to worry about the graphs. I'm going to give you the graphs when you need them. And the last thing we're going to do here is area. So we're going to do the calculus with polar coordinates, and we're going to look at area next. So I'm going to cut this video off here. We're going to have one more part with our area formula here, and 2 examples, and then that will finish the course. Okay, so we'll come back, and then I'll have I should have some review videos, or at least a discussion of with you regarding the review for the final. All right, so we'll see you for the final topic whenever you're ready.